In 7.2, we've talked a lot about how to integrate between curves. In each example so far, we've talked about how to integrate with respect to x. Now I'm going to introduce how to integrate with respect to y. So sometimes the boundaries of the regions are more easily described by functions in terms of y rather than terms in x. If you notice from the last example, determining the equations was kind of a pain, and then determining the endpoints was also kind of difficult, and we had to break up the region into two pieces. Sometimes when you integrate in respect to y, you don't have to worry about that. So previously, we've looked at integrating with respect to x, where this vertical line represents the areas that we're adding up of each rectangle, and then right here, your lower bound changes. But you see how you have this integral, and you have to add it to this integral. Well, what we can do is if we integrate with respect to y, we can just take the integral like this. And the bounds are going to be this line and this curve, and we don't have to change the limits of integration, and we don't have to change anything. We just integrate with respect to y instead of integrating with respect to x. So to find this area, again, you would have to use this integral plus this integral. With respect to y, the bigger function is always bigger than the smaller function, which in respect to x, that didn't happen. So we're going to determine the area of the region in example 4 by integrating with respect to y. So recall that this was the graph from example 4. And recall that our functions were y equals the square root of x and y equals x minus 2. So this graph right here is y equals the square root of x. So if we were to solve that for x, we would get x equals y squared. This graph right here was y equals x minus 2. So x is equal to y plus 2. Because we're going to integrate with respect to y, we need all our variables in terms of y. It's also important to remember that this coordinate right here was 4, 2. We're going to be looking at the y value this time. And my smallest y value is 0. So we're going to be integrating from this value here all the way up to this y value right here. So step 1 is to rename the curves in terms of y by solving for x. So if you have y equals the square root of x, you get that x is equal to y squared by squaring both sides. And if y is equal to x minus 2, you get x is equal to y plus 2. Step 2 is to determine the limits of integration. Well, by just looking at our graph, we determined what they were, but let's do it by hand. So we have x is equal to y squared, and we have x is equal to y plus 2. So we set those equal to each other, just like when we solve for x's, y plus 2. And then we go ahead and solve. So y squared minus y minus 2 equals 0. And we get y minus 2, y plus 1. So you get y equals 2 and y equals negative 1. Well, y equals negative 1 does not work because it's not in the first quadrant, which is where our example is. So y equals 2 is going to be our upper limit, and we know our lower limit is y equals 0. So what we need to do now is determine which function is larger. And I put larger in quotation marks because the function itself is not actually bigger, but we're trying to determine which function do we subtract from which. Well, just looking at the graph, we know that y plus 2 is strictly greater than or equal to y squared on the interval 0, 2. So by looking back at the graph, you see that this red function here is strictly larger than this function right here. Typically, just like when we would do the top minus bottom, when we integrate with respect to y, it's right minus left. So this is going to be our f of y function, which is our right function. And this is our g of y, which is our left function. And then step 3 is to set up an integral and solve. So we're going to get our integral from 0 to 2, because those are our y limits. And the right function was y plus 2. And the left function was y squared dy. And now that's all left to do is just to integrate. And you'll notice that when we solve it, we end up with the same answer as when we split up the integral and integrated it with respect to x. Now on your own, I want you to try to determine the area enclosed in the region between y squared equals x plus 1 and y squared equals 3 minus x. And I want you to try to do it by integrating with respect to y. It's very helpful to graph these, so I really do recommend that you graph these on your calculator. Your calculator really only thinks in x, so you might have to solve for y. Don't forget the plus or minuses to fully graph these, or use a online graphing calculator. Here is the image of the two graphs, if that would also help. Alright, so here we go. It's important to note that this graph right here represents x equals 3 minus y squared. And then this graph here represents x equals y squared minus 1. So we take our two graphs, and we're going to do some algebra with them. And we have x is equal to y squared minus 1 as our green graph, and x is equal to 3 minus y squared as our blue graph. So we need to determine which one is on the right and which one is on the left. Well, we have y squared minus 1, and you notice that this is on the left side. So this is strictly less than 3 minus y squared. So now we need to determine those intersection points. And to do that, we set both of them equal to each other. So we get y squared minus 1 is equal to 3 minus y squared. You are also able to do this on your graphing calculator by graphing them and then tracing them out. But let's do it by hand. So we get 2y squared is equal to 4. So y squared is equal to 2. So y is equal to plus or minus the square root of 2. So then this gives you y equals negative square root of 2 and y equals positive square root of 2, where this is going to be our lower limit and this is our upper limit. Now all we need to do is set up the integral and solve. So we get that this is the integral from negative square root of 2 to square root of 2 of 3 minus y squared minus y squared minus 1 dy. We get this because 3 minus y squared is our right graph and y squared minus 1 is our left graph. So this becomes negative square root of 2 square root of 2, 3 minus y squared minus y squared plus 1 dy. So integral negative square root of 2 square root of 2, negative 2y squared plus 4 dy. And now all you have to do is work this out. So after integrating that and combining like terms, you get 16 squared to 2 over 3, which is approximately 7.542 units squared.